Welcome to This Explainer. Today, we're looking at the ocean a bit differently. Instead of just seeing a massive body of water, we're going to treat it like a giant, density-driven machine. To really understand how this planetary engine works, we actually need to reverse engineer its chemical recipe from the ground up.
Here's our flight plan for today. We'll start with the recipe of seawater, then move on to the constant proportions principle. After that, we'll map surface salinity across latitudes, dive deep into the halocline, and wrap up with density, thermoclines, and pycnoclines.
Let's jump right into part 1, the recipe of seawater.
So, when oceanographers talk about the ocean's recipe, they're mostly talking about salinity. And we don't just mean how salty it tastes. Salinity is precisely defined as the total amount of solid inorganic material dissolved in water. On average, the ocean sits right around 35 parts per thousand. Think of it like this. If you scoop up a typical 1,000-gram sample of average seawater, it's not actually 1,000 grams of pure water. You've got exactly 965 grams of water and 35 grams of dissolved solids.
And if you look at how that breaks down, it's pretty heavily skewed. Just 6 major ions make up over 99% of all the dissolved salts in the entire ocean. The absolute heavyweights here, chloride and sodium, which, makes perfect sense as to why seawater tastes exactly like table salt. But you've also got sulfates, magnesium, calcium, and potassium in the mix. The sheer precision of this chemical blend is really the foundation for everything the ocean does. Which brings us to part 2, the constant proportions principle. Now, here's where it gets really interesting. The principle of constant proportions states that the ratio of these major ions to each other remains exactly the same, totally regardless of the total salinity. So whether you're taking a sample from a slightly fresher bay or an intensely salty basin, the percentage of chloride to sodium to magnesium, it never shifts. This is a massive deal for scientists because it means they can calculate the total salinity of any ocean sample just by measuring a single ion, which is usually chlorine.
Of course, this kind of consistency doesn't just happen by magic. It exists because these major ions are what we call conservative constituents. Basically, they're chemically non-reactive in seawater. This gives them staggering residence times, meaning they stay dissolved for literally millions of years before cycling out. That is a huge contrast to non-conservative constituents, things like oxygen, carbon dioxide, or nutrients like nitrogen and phosphorus. Those have residence times of way less than 1,000 years, simply because they're constantly being consumed and expelled by biological life cycles and seasonal shifts.
Moving on to part 3, surface salinity across latitudes.
Let's zoom out to a global view. Looking at this satellite heat map of surface salinity, the darker the orange and red areas, the saltier the water. The cooler blues and purples are fresher. Now, your first instinct might be that the hottest part of the planet, the equator, must have the saltier water, right? But look at those dark orange regions. They are completely concentrated in the mid-latitudes right around the tropics of Cancer and Capricorn. Check out that massive bright patch sitting right in the middle of the Atlantic.
So why does the global map look like that? Well, salinity isn't just about pure heat. It's a constant battle between evaporation, which removes pure water and leaves the salt behind, and precipitation, which dumps pure fresh water right back in. Salinity actually peaks at the tropics because those areas see incredibly high evaporation but very low rainfall. Down at the equator, sure, evaporation is intense, but massive, heavy tropical rain offsets it, diluting the surface and keeping the salinity much lower. And naturally, salinity plummets at the poles. That's driven by super low evaporation, massive freshwater runoff from rivers, and, of course, melting sea ice.
Let's dive a bit deeper with part 4, diving deep, the halocline.
As we move vertically down into the water column, we hit something called the halocline. Think halo for salt and cline for slope. This is a specific vertical zone where salinity changes incredibly rapidly and sharply with depth. And the wild thing is, depending on your global starting point at the surface, the chemical profile completely inverts itself as you dive.
Let's actually break those curves down. If you drop a probe in the low latitudes, like the tropics, you're starting with highly saline surface water. But as you descend through that halocline, usually between 200 and 1,000 meters down, the salinity rapidly decreases. On the flip side, if you drop a probe at the high latitudes near the poles, you start in relatively fresh water because of all that melting ice. But as you dive through the halocline there, the salt content sharply increases. Here's the real magic, though. Notice how, regardless of where you start on the globe, once you get below 1,000 meters, both of these profiles magically merge and stabilize right around 35 parts per thousand. The deep ocean is just incredibly uniform.
Which brings us to our final section, Part 5, Density, Thermoclines, and Pycnoclines. The really crucial takeaway here is how this salinity interacts with other variables to dictate the ocean's ultimate physical structure, specifically its density layers. Density is the boss here. It dictates whether a massive body of water is going to float at the surface or plunge all the way to the abyssal depths, and it's driven by three main variables. Temperature has the greatest overarching effect globally. Salinity is a close second, though it actually becomes the dominant factor in polar regions where the temperature is already stable year-round. Pressure? It has the absolute least effect, really only slightly compressing water at the most extreme depths.
Since temperature is the primary driver of density, we really have to look at the thermocline. In warm, lower-latitude regions, the sun heats up the ocean's surface, which creates this nice, well-mixed layer of warm water down to about 300 meters. But once you pass that mark, sunlight just can't penetrate, so the temperature rapidly and steeply plummets in this massive drop-off known as the thermocline, right before you hit the near-freezing temperatures of the deep ocean.
And that steep thermal cliff gives birth to the pycnocline. Pycno just means density. Because cold water is significantly denser than warm water, the sudden thermal drop of the thermocline perfectly mirrors a massive, sudden spike in water density. What this does is create a physical, albeit invisible, barrier right in the water column. It heavily stratifies the ocean, physically preventing the warm, less dense surface water from mixing with the frigid, high-density deep water below it. This stratification is literally the beating heart of our ocean machine. Remember how temperature and salinity control density? Well, in the polar regions, surface water gets incredibly cold, and as sea ice forms, it leaves puce salt behind. That drastically spikes the salinity of the surrounding water. Cold plus salty equals extreme density. This violently dense water mass becomes so heavy that it literally sinks beneath the less dense masses around it, plunging straight to the ocean floor. And that sinking action at the poles acts like a giant pump, pulling surface water in to replace it, which drives the deep, slow global currents that regulate our planet's climate over thousands of years.
All of this leaves us with a critical, undeniable question to take away from this explainer. We just mapped out exactly how perfectly balanced this density machine is. But right now, rising global temperatures are fiercely heating that surface layer, and massive influxes of melting polar ice are actively diluting the surface salinity. Both of these actions fundamentally alter the precise density equations we just walked through. If we change the temperature and the salinity, we change the pycnocline. So, as this invisible density engine shifts, how is it going to reshape the global currents that sustain the climate, and ultimately, life on Earth? Thanks so much for joining me for this explainer. I'll leave you to think on that.